Look up at the night sky. What do you see? A scattering of bright pinpricks twinkling against the darkness. It's beautiful, isn't it? But here's the thing. Those stars you can see are just the tiniest fraction of what's really out there. The universe is teeming with stars we'll never lay eyes on, no matter how hard we stare. Some are too faint, too far, or simply hidden behind cosmic curtains of dust and gas. Others defy our very understanding of light itself, lurking in the shadows of space, invisible by their very nature. These are the hidden stars, the ones that don't just escape our sight but challenge everything we thought we knew about the cosmos. Think about that for a second. We're surrounded by a silent symphony of celestial wonders we can't even perceive. Stars that burn with colors beyond our vision. Stars so dense they bend light into oblivion. Stars that flicker in and out of existence like cosmic ghosts. They're out there right now, whispering secrets we're only beginning to unravel. And the wildest part, some of them might be closer than we think, hiding in plain sight, disguised as empty patches of sky. It's like living in a house where the walls are lined with hidden doors. You just don't know how to open them yet. This is where the real magic of astronomy begins. Not with what we can see, but with what we can't. These hidden stars aren't just gaps in our knowledge, they're clues to the universe's greatest mysteries. They hold the keys to understanding how galaxies form, how matter behaves under extreme conditions, even how time itself might warp around them. So buckle up, because today we're pulling back the cosmic veil. We're diving into the stories of 30 stars you'll never see but whose existence will leave you utterly spellbound. From phantom stars that vanish without a trace to dark giants lurking at the edge of reality, this journey will change how you see the night sky, or rather, how you see the darkness between the stars. Let's begin. Some stars don't just hide, they hunt. Meet the Black Widow Pulsar, a cosmic predator lurking in the constellation Sagittarius, nearly 6,500 light-years away. This isn't your average star, it's a neutron star, the crushed corpse of a supernova, spinning at a dizzying 700 times per second. But what makes it truly terrifying is what it's doing to its neighbor. Like its namesake spider, this pulsar is slowly devouring its companion star, stripping it layer by layer with its monstrous gravitational pull. How does something so violent stay invisible? Simple, it doesn't play by the rules of light. The Black Widow Pulsar doesn't glow like ordinary stars. Instead, it's a gamma-ray factory, blasting out high-energy radiation that our eyes can't detect. Optical telescopes see nothing but empty space where it lurks. Yet, thanks to specialized instruments like NASA's Fermi Gamma-Ray Space Telescope, astronomers caught its deadly signal, a pulse so regular it could set a cosmic clock. The real twist, this pulsar doesn't just consume, it annihilates. The energy it unleashes is so intense, it's vaporizing its companion into a ghostly cloud of plasma. One day, there'll be nothing left, and here's the chilling part. There could be countless more like it, hidden in the darkness, rewriting what we thought we knew about stellar relationships. The Black Widow isn't just a star, it's a warning. The universe is full of killers we can't even see. Now imagine a star within a star, a cosmic Russian nesting doll hiding in plain sight. That's the Thorne-Żytkow Object, one of the universe's most bizarre hypothetical creations. Picture a swollen red giant, its outer layers stretching millions of miles but lurking at its heart. Not the usual fusion furnace, but the crushed remnant of a dead star, a neutron star. This isn't science fiction, it's a stellar collision frozen in time, where two stars became one in the most unsettling way possible. Why can't we see these cosmic chimeras? The answer lies in their perfect disguise. From the outside, a Thorne-Żytkow object looks almost identical to a regular red giant. Same ruddy glow, same immense size, but peer closer, or rather, listen closer, because these stars sing differently. Their internal turmoil creates unique chemical fingerprints, like unusually high amounts of lithium or rubidium that might betray their true nature. The problem, spotting those subtle clues, requires analyzing starlight with impossible precision across unimaginable distances. It's like trying to identify a whisper in a hurricane. The scientific debate around these objects is fiercer than a supernova. Some researchers argue we've already found candidates, stars like HV 2116 in the Small Magellanic Cloud, whose strange composition makes astronomers raise an eyebrow. Others insist we're seeing cosmic mirages, ordinary stars with odd chemistry. The irony, even if we confirm their existence, Thorne-Żytkow objects might be the universe's most tragic stars. They're not eternal. That neutron star core, it's slowly spiraling inward, destined to either trigger a cataclysmic explosion or vanish silently into oblivion, leaving no trace of its cannibalistic past. Here's what haunts scientists. If these hybrids exist, they rewrite the rules of stellar evolution. They're proof that stars don't just live and die, they sometimes merge, creating monstrosities that defy classification. And somewhere out there, hidden among the familiar constellations, one of these invisible abominations might be pulsing quietly, waiting for us to decipher its secrets. What if the universe hid stars we can't even imagine, structures built not from ordinary matter, but from the mysterious substance we call dark matter? Picture a celestial body that doesn't shine, doesn't burn, and doesn't interact with light in any way. These hypothetical dark matter stars could be lurking throughout the cosmos, massive yet utterly invisible, defying every rule of stellar physics we know. The concept begins with dark matter's strange properties. Unlike normal matter, it doesn't emit, absorb, or reflect light, hence the name. But under extreme conditions, some theories suggest dark matter particles could collide and annihilate, releasing energy without any visible glow. Imagine a star where this invisible process replaces nuclear fusion. Instead of a fiery core, it would have a dark, roiling heart, generating heat and gravity while remaining completely undetectable to telescopes. Could such a star actually form? The math suggests it's possible. In the early universe, vast clouds of dark matter might have collapsed under their own gravity, pulling in enough material to ignite annihilation reactions. These structures wouldn't just be invisible, they could dwarf even the largest supergiants with masses hundreds of times greater than our Sun. Some models propose they'd have a ghostly halo of normal matter around them, like a faint echo of their presence. The hunt for these phantoms is as tricky as it gets. Without light to guide us, astronomers rely on indirect clues, gravitational lenses bending space more than expected, unexplained heat signatures in deep space, or strange motion patterns in star clusters. One tantalizing candidate, a bizarre object called Draco, sits in our own galactic backyard. Its gravitational influence suggests something massive is there, yet no visible star matches its profile. Could it be a dark matter star? The debate rages on. Here's the unsettling truth. If these stars exist, they'd rewrite our cosmic playbook. They'd prove dark matter isn't just a passive backdrop to the universe. It can clump, ignite, and shape reality in ways we're only starting to grasp. And somewhere in the darkness between the stars, an entire invisible stellar population might be watching us, silent and unseen. Some stars don't just hide, they flee. Streaking through the cosmos at speeds that defy imagination, hypervelocity stars are celestial fugitives, ejected from our galaxy with such force that they are destined to drift alone through the intergalactic void. And here's the catch: most of them are utterly invisible to us, not because they're cloaked or mysterious, but because they're too faint, too distant, or moving so fast that they've already left our observational reach. Take a moment to picture the sheer violence behind their escape. These aren't leisurely wanderers, they're cosmic bullets. Some were slingshotted away by the supermassive black hole at the Milky Way's core, a gravitational monster that can rip binary star systems apart, flinging one star into oblivion while consuming the other. Others are survivors of supernova explosions, their partner stars detonating with such force that the survivors were catapulted into the darkness like interstellar shrapnel. The fastest among them race outward at over 2 million miles per hour, fast enough to cross the distance from Earth to the Moon in just 7 minutes. Spotting these renegades is like trying to photograph a speeding bullet in near-total darkness. Their light is often drowned out by the glow of the Milky Way, or stretched into invisibility by their extreme velocity. So how do we even know they exist? Astronomers play cosmic detectives, tracking subtle distortions in starlight or chasing the gravitational ripples these stars leave in their wake. One telltale clue: their motion defies the Milky Way's rotation, cutting across the galactic current like salmon swimming upstream. The most famous escapee, affectionately dubbed the outcast star, was discovered racing away from us at nearly 900,000 miles per hour. It's a solitary white dwarf, its light so dim it took years of painstaking observation to confirm its trajectory. But here's what's haunting: for every hypervelocity star we've spotted, there are likely thousands more already beyond our grasp, their faint glow lost in the vastness between galaxies. What's truly humbling is realizing these invisible fugitives are rewriting galactic history. Their paths trace back to ancient cataclysms, collisions, explosions, and close calls with black holes that occurred millions of years before humans even looked up at the night sky. And somewhere out there, another star is being hurled into the abyss right now, its journey beginning in violence and ending in perfect, unobserved solitude. Long before the first familiar stars flickered to life, the universe may have birthed monsters, colossal, unstable behemoths known as quasi-stars. Picture a star so massive it makes today's supergiants look like specks of dust, stretching hundreds of millions of miles across. But here's where things get bizarre. At its core, instead of the usual nuclear fusion, there'd be a ravenous black hole, feeding on the star's own flesh to keep it shining. These aren't just stars with black holes inside them, they're cosmic Ouroboros devouring themselves to stay alive. Why would such a thing even exist? Rewind to the early universe, a time when gas clouds were denser and heavier elements hadn't yet formed. Under those extreme conditions, collapsing gas might have formed stars with masses thousands of times greater than our Sun. Normally, a star that massive would tear itself apart in a supernova almost instantly, but quasi-stars had a twisted survival mechanism. As their cores collapsed into black holes, the sheer pressure of infalling material would have generated enough outward radiation to halt total collapse. The result, a balancing act of cosmic proportions, a black hole feasting on its host star's inner layers, while the star's outer layers, heated by the energy of this monstrous meal, glowed fiercely enough to hold the entire structure together. Spotting these primordial titans today, impossible. Their very nature makes them ghosts of cosmic history. Unlike modern stars, quasi-stars wouldn't have left behind neat stellar remnants or nebulae. Once the black hole at their core consumed enough material, the outer layers would have dissipated, leaving behind only the growing black hole, seeds for the supermassive monsters we now find at the centers of galaxies. And here's the chilling part: some astronomers suspect these quasi-stars could explain the existence of early supermassive black holes, objects so enormous they shouldn't have had time to form in the young universe. Perhaps they didn't form gradually, they were born inside these stellar furnaces, handed a head start by the cannibalistic stars that spawned them, the most mind-bending implication. If quasi-stars existed, they'd rewrite the story of how black holes grow. Instead of slowly accumulating mass over eons, supermassive black holes might have begun as voracious infants, fed by the dying gasps of the universe's first and most unnatural stars. And somewhere in the depths of space, the descendants of those black holes still lurk, silent monuments to an era when stars didn't just shine, but swallowed themselves alive. At the edge of our cosmic awareness lurk the ultimate invisible roamers, rogue black holes, the dark remnants of long-dead stars cast adrift in the interstellar void. Unlike the supermassive black holes anchored at galaxy centers, these lone wanderers don't announce their presence with glowing accretion disks or violent jets. They drift silently through the darkness, invisible by their very nature, detectable only by the gravitational chaos they leave in their wake. Imagine a predator that doesn't just hide in the shadows, it is the shadow, its presence betrayed only when it reaches out to twist the fabric of space itself. The key to unmasking these phantoms lies in a phenomenon called gravitational microlensing. Here's how it works. When a rogue black hole passes between us and a distant star, its immense gravity bends the star's light like a cosmic magnifying glass. The star's brightness spikes suddenly, then fades, a telltale flicker lasting mere hours or days. No other object warps spacetime with such precision. It's like spotting a hidden burglar by the fleeting distortion of a security camera's image, except the burglar is 1,000,000 times the sun's mass and the camera is the fabric of reality. But microlensing isn't just a cosmic parlor trick. It's revealed terrifyingly close calls. In 2018, astronomers tracking a star 8,000 light-years away watched its light distort in a pattern suggesting a rogue black hole had drifted within just 20 light-years of our solar system. To put that in perspective, if this darkest of tourists had veered even slightly closer, its gravity could have sent comets hurtling toward Earth or yanked planets from their orbits, all without us ever seeing the culprit. The scariest part, we've likely only spotted a fraction of them. Current estimates suggest millions of rogue black holes could be prowling our galaxy, relics of ancient supernova that kicked their remnants into the abyss. Some might even be primordial, born in the chaos of the Big Bang, older than stars themselves. And while the odds of a direct collision are infinitesimal, their gravitational influence could destabilize entire star systems over cosmic time. What's truly humbling is realizing these invisible drifters are rewriting the rules of cosmic dynamics. They're proof that black holes aren't just static traps at galaxy centers. They're active, restless travelers, shaping the universe in ways we're only beginning to map. And somewhere out there, another one is sliding through the dark right now, its passage marked only by the faintest ripple in the starlight. Between the blazing stars and wandering planets lies a shadowy realm of cosmic misfits, objects too massive to be planets yet too small to truly shine. These are brown dwarfs, the universe's failed stars, doomed from birth to wander the darkness. Imagine a celestial body born with all the ingredients for stardom: hydrogen, gravity, the works, but lacking just enough mass to spark the fusion furnace that makes stars burn. The result, a perpetual twilight object radiating only a faint whisper of heat, more akin to a smoldering ember than a blazing fire. Spotting these cosmic phantoms is like searching for a black cat in a coal cellar. Their visible light is virtually non-existent, but in the infrared spectrum they betray a subtle glow, a thermal fingerprint of their residual warmth. That's where instruments like the James Webb Space Telescope become game changers. Unlike Hubble, which primarily sees invisible light, Webb's infrared eyes pierce through the obscurity, revealing brown dwarfs by their heat signatures rather than their light. Some of the most fascinating discoveries defy expectations. Take WISE 0855-0714, a brown dwarf so cold its temperature hovers around -10 degrees Fahrenheit colder than a winter night in Antarctica. It drifts alone just 7 light-years away, making it one of the Sun's closest yet most elusive neighbors. Without Webb's sensitivity, we'd have never noticed this frozen relic lurking practically in our cosmic backyard. But brown dwarfs aren't just celestial curiosities, they're rewriting the rules of planetary and stellar formation. Some host violent storms with winds faster than hurricanes, their turbulent atmospheres streaked with molten iron and silicate clouds. Others exist in gravitational limbo, orbiting so far from any star that they blur the line between rogue planet and failed star. And then there's the chilling possibility that many more, perhaps billions, drift unseen between the stars, dark and solitary. Here's the twist: some brown dwarfs might not be alone. Astronomers have spotted pairs orbiting each other, locked in a slow dance with no star to illuminate them. Others may harbor planets of their own, worlds doomed to eternal twilight under a dim, cherry-red sky. The universe, it seems, has a flair for the dramatic crafting entire systems where the primary, sun, can't even manage a proper glow. What's truly humbling is realizing these objects are cosmic missing links, bridging the gap between stars and planets. They're proof that nature doesn't follow tidy categories, it thrives in the messy in-between. And with every new discovery, we're forced to confront an unsettling truth. The darkness between the stars isn't empty. It's teeming with shadows we're only beginning to perceive. Deep in the swirling theories of cosmic mysteries lies a proposition so unsettling it sounds like science fiction. What if our sun isn't alone? Lurking somewhere beyond the edges of our solar system, a dark companion might circle our star in a slow, silent dance, its presence revealed only by catastrophe. This is Nemesis, the hypothetical Death Star, a dim red dwarf or brown dwarf theorized to orbit the Sun every 26 million years, triggering waves of extinction each time it swings close enough to disturb the icy bodies at the solar system's fringe. The idea emerged from a chilling pattern in Earth's fossil record. Paleontologists noticed mass extinctions like the one that wiped out the dinosaurs seemed to follow a rough 26 million year cycle. In the 1980s, scientists proposed a terrifying explanation. Something massive, something unseen, periodically nudges the Oort cloud, that distant shell of icy debris surrounding our solar system. The gravitational disturbance would send comets hurtling inward like a cosmic hailstorm, some inevitably striking Earth with apocalyptic force. Nemesis earned its name for a reason. It wouldn't just be a companion. It would be an executioner, so why haven't we found it? The challenges are staggering. Nemesis, if it exists, would be faint, likely a cool red dwarf or even a failed brown dwarf emitting almost no light. Its orbit would be staggeringly wide, stretching perhaps 1.5 light years from the Sun at its farthest point, making it a needle in the cosmic haystack. Even our most powerful telescopes struggle to spot cold, dim objects at such distances, especially when we don't know exactly where to look. The evidence remains tantalizingly contradictory. Infrared surveys like NASA's A WISE mission have scanned the skies for heat signatures of hidden stellar objects, ruling out some possibilities but leaving gaps. Some researchers point to odd gravitational tugs on objects in the outer solar system as potential clues, while others argue these could simply be statistical noise or unseen dwarf planets. The math, too, is contentious. Stellar binaries are common in the galaxy, but Nemesis's proposed orbit would be exceptionally wide and unstable over cosmic time. What's fascinating is how this theory blurs the line between astronomy and paleontology. It forces us to consider that Earth's biological history might be etched not just by the gradual forces of evolution, but by the invisible machinations of a star we've never seen. The debate rages on, with some scientists dismissing Nemesis as a cosmic ghost story, while others insist we simply haven't looked hard enough. Here's the haunting possibility: even if Nemesis doesn't exist, something else might. Our solar system could harbor unseen dwarf stars, rogue planets, or other dark travelers hiding in the vastness just beyond our sight. The search continues, not just for a Death Star, but for any shadowy neighbors altering the destiny of life on Earth, silent partners in the Sun's lonely journey through the galaxy. Some stars wear cosmic masks, thick, swirling shrouds of carbon dust so dense they vanish from sight. These are carbon stars, aging giants in their final fiery chapters, literally burying themselves in the soot of their own demise. As they burn through their nuclear fuel, they undergo a bizarre transformation. Their outer layers become factories for carbon molecules, churning out dark, smoky particles that eventually cocoon the entire star. To optical telescopes, they might as well not exist, their light smothered beneath blankets of their own creation. But peel back that veil, and you'll uncover one of the universe's most poetic cycles of destruction and rebirth. Carbon stars are stellar alchemists, forging the very elements that make life possible. Every speck of carbon in your body, every diamond in Earth's crust, likely began in the heart of a star like this. The irony, they're too good at their job. The more carbon they produce, the more effectively they cloak themselves, becoming prisoners of their own abundance. This is where infrared astronomy becomes our Rosetta Stone. Carbon dust might block visible light, but it can't hide the heat. Instruments like the James Webb Space Telescope see these stars not by their glow, but by their warmth, the same way you might spot a person's silhouette in a foggy room by their body heat. And what we've found is astonishing. Some carbon stars are surrounded by intricate, nested shells of dust, like tree rings telling the story of their violent final millennia. Others show bizarre chemical fingerprints, with molecules like cyanide and silicon carbide swirling in their atmospheres, ingredients for future planets, and perhaps even life brewing in the darkness. The most mind-bending discovery, some carbon stars are essentially cosmic matryoshka dolls, hiding other stars within their dusty embrace. In binary systems, a carbon star's expelled material can wrap around its companion, creating a celestial Russian nesting doll visible only in infrared. These systems might eventually give birth to exotic stellar hybrids or even supernova, their carbon-rich debris seeding future generations of stars and planets. Here's the humbling truth: without these hidden giants, the cosmos would lack the building blocks for rocks, oceans, or even DNA. They're the universe's unseen recyclers, turning dying gas into the raw materials for new beginnings. And somewhere out there, right now, another carbon star is wrapping itself in darkness, its final act of stellar alchemy already setting the stage for worlds yet to be born. Among the silent majority of the cosmos, white dwarfs are the unseen dead stellar ghosts glowing faintly with leftover heat, their brilliance long faded. These remnants of sun-like stars make up nearly 97% of all stars destined to exist in our universe, yet most slip beneath our notice simply because they've run out of fuel to burn brightly. Picture the ember of a once roaring campfire, still warm but no longer aflame. That's a white dwarf, a celestial cinder, packing the mass of a star into a sphere no larger than Earth. What makes them so elusive isn't just their size, it's time. A white dwarf doesn't explode or vanish dramatically. Instead, it cools with agonizing slowness, its surface temperature dropping by mere degrees over millennia. The oldest among them are barely visible even to our most sensitive telescopes, radiating only in the faintest infrared. Some, like the companion star to Sirius, give themselves away by tugging on brighter neighbors. Others drift alone, their presence betrayed only when they pass in front of distant stars, their gravity bending light in telltale ways, but the real mystery lies in what they're becoming. Given enough time, far more than the current age of the universe, a white dwarf will cool completely, fading into a black dwarf, a cold, dense crystal of carbon and oxygen, invisible against the cosmic backdrop. The universe hasn't existed long enough for any black dwarfs to form yet, which means every white dwarf we see is a preview of the sun's eventual fate, frozen mid-transformation. Yet, even in their fading, these ghosts hold surprises. Some are cosmic vampires, siphoning material from companion stars until they erupt in thermonuclear explosions as Type 1, a supernova. Others, like the bizarre diamond star BPM 37093, are crystallizing into spheres of crystallized carbon, literal celestial diamonds millions of carats in size. And then there are the magnetic anomalies, white dwarfs with magnetic fields billions of times stronger than Earth's, twisting their atmospheres into bizarre chemical storms. The chilling truth, these stellar tombstones are the future. Long after the last main sequence stars burn out, white dwarfs will dominate the cosmos, their slow fade marking the universe's descent into darkness. They're reminders that even in death, stars don't vanish, they linger, whispering their stories in wavelengths only the most patient observers can hear. Long before galaxies spiraled into existence, before planets took shape around stable suns, the universe hosted its first generation of stars, and they were unlike anything we see today. Born from pristine clouds of hydrogen and helium, these population 3 stars were the cosmic pioneers, lighting up the darkness when the universe was just a few 100 million years old. But here's the catch: despite shaping the cosmos as we know it, not a single one has ever been observed. They remain theoretical ghosts, their existence inferred only by the chemical fingerprints they left behind. Why are these primordial giants so elusive? The answer lies in their brutal fate and their unnatural purity. Without heavier elements to help them shed heat, population 3 stars likely grew to staggering sizes, some reaching hundreds of times the mass of our Sun. Imagine a star so colossal its surface temperature exceeded 100,000 degrees, blazing with ultraviolet fury, but such extremes came at a cost. These stars burned fast and died young, their cores collapsing into cataclysmic supernova or even direct black holes within a few million years, a blink in cosmic time. Their deaths weren't just violent, they were transformative. The explosions seeded the universe with the first heavy elements, forging carbon, oxygen, and iron in their furnaces, building blocks for future stars, planets, and life itself. Yet the irony is profound. By enriching the cosmos, they ensured no star like them could ever form again. Later generations, like our Sun, owe their existence to the ashes of these vanished behemoths. But how do we hunt for stars that left no survivors? Astronomers play cosmic archaeologists, searching for traces in the most ancient light. The James Webb Space Telescope peers into the deepest past, hoping to spot the ultraviolet glow of a population 3 stars death throws in distant galaxies. Others study quasars whose light passed through primordial gas clouds, revealing absorption lines that hint at the chemistry these stars created. The most tantalizing clue: a peculiar group of ultra-faint dwarf galaxies orbiting the Milky Way. These relics from the early universe contain stars almost devoid of heavy elements, possible second-generation offspring of population 3 giants. By studying them, we might reverse engineer the properties of their long-dead progenitors. Here's the haunting truth: if we ever confirm their existence, it won't be by seeing them. It'll be by recognizing the void they left behind, a universe forever altered by stars that shone briefly, died violently, and vanished without a trace. Their legacy isn't in the light we observe, but in the darkness they illuminated for everything that came after. Picture the aftermath of a supernova, a cosmic battlefield where a star's core has collapsed into a sphere just 12 miles wide, yet so dense a teaspoon of its material outweighs Mount Everest. Now imagine that remnant spinning silently in the void, its deadly radiation beams sweeping through space like a lighthouse nobody sees. This is the fate of isolated neutron stars, the universe's darkest sentinels. Unlike their pulsar cousins whose brilliant beams we detect when aligned with Earth, these lone wolves refuse to announce themselves. They're stellar ghosts radiating nothing visible to our eyes, their lethal energies pointed harmlessly into the abyss. Yet even the stealthiest predators leave traces. For neutron stars, it's the heat of their unimaginably hot surfaces around 1 million degrees leaking into space as X-rays. Satellites like NASA Chandra X-ray Observatory have become our night vision goggles, spotting these faint thermal signatures against the cosmic background. One such discovery, Calvera, floats eerily close at just 2,000 light-years away, its X-ray glow betraying a presence that optical telescopes completely missed. The numbers are staggering. For every pulsar we've spotted, there could be 10 to 100 more neutron stars hiding in the darkness, their beams never crossing Earth's path. But heat isn't their only giveaway. When isolated neutron stars tear through dense molecular clouds, something they do at terrifying speeds, they can trigger shockwaves visible in radio wavelengths. Others warp spacetime itself, creating gravitational lenses that briefly magnify background stars in predictable patterns. Then there's the ultimate cosmic detective tool, gravitational wave observatories. When two neutron stars spiral together in a death spiral, like the event detected in 2017 by LIGO, they send ripples through spacetime that reveal their nature regardless of their orientation. The most unsettling part, some of these silent killers might be closer than we think. A neutron star born in the same supernova that created the Geminga pulsar, just 800 light-years away, could be drifting unseen through our galactic neighborhood right now. And if one passed within a few light-years of Earth, its magnetic field alone could strip away our ozone layer without warning. Here's what keeps astronomers up at night. These isolated neutron stars are cosmic landmines, remnants of stellar explosions we didn't witness, their positions and velocities unknown. Every new detection rewrites our understanding of how many dead stars are out there, and how many more remain invisible, their lethal beams sweeping through space unseen and unheard. Even the most reliable cosmic yardsticks can be fooled. Meet the Cepheid variable stars that pulse with clockwork regularity. Their brightness fluctuations so predictable they've become astronomy's gold standard for measuring distances across the universe. But interstellar dust, that silent thief of starlight, has been playing tricks on us. Some of these vital distance markers are hiding in plain sight, their true brightness muffled beneath layers of cosmic soot, throwing off measurements that underpin our entire cosmic map. Here's why it matters. A Cepheid's pulse rate directly correlates with its intrinsic brightness. Measure how fast it flickers, and you know how luminous it should be. Compare that to how dim it appears from Earth, and voila, you've calculated its distance. This method famously helped Edwin Hubble prove galaxies exist beyond the Milky Way. But dust clouds along our line of sight absorb and scatter a Cepheid's light, making it seem farther away than it really is. The effect is like trying to gauge a lighthouse's distance through fog. You'll overestimate how far it is because you can't see its full glow. The solution: astronomers have turned to multi-wavelength espionage. Dust affects shorter wavelengths of light, like visible blue, more than longer infrared waves. By observing Cepheids across this spectral spectrum, scientists can essentially subtract the dust's dimming effect. The Spitzer Space Telescope revolutionized this approach, its infrared eyes revealing Cepheids previously misclassified due to dust deception. One standout case is RS Puppies, a Cepheid wrapped in such thick dust its visible light dims by 60%. Spitzer's infrared data corrected its distance measurement by over 1,000 light-years, a cosmic margin of error with ripple effects across entire galaxies. But the plot thickens. Some Cepheids aren't just cloaked, they're shape-shifters. Their pulsations can stir surrounding dust into asymmetrical shells, creating mirage-like distortions. The European Space Agency's Gaia mission has exposed these quirks by precisely tracking Cepheids' motions in 3 dimensions, revealing how their movement through dusty regions warps our view. It's a reminder, even the steadiest cosmic beacons don't give up their secrets easily. The stakes couldn't be higher. Cepheids calibrate the cosmic distance ladder, which in turn refines our measurement of the Hubble constant, the universe's expansion rate. Discrepancies in this rate hint at unknown physics, possibly dark energy's influence or even flaws in our understanding of gravity. Every dust-hidden Cepheid we unmask sharpens the tools we use to probe these mysteries. So while these stars may flicker behind cosmic veils, their hidden truths are rewriting the story of the universe one wavelength at a time. Some stars don't fade, they vanish in plain sight. Wolf-Rayet stars are cosmic specters, enormous beasts so volatile they're literally disintegrating before our eyes, cloaking themselves in the shredded remains of their own outer layers. Picture a star 20 times more massive than the Sun, burning so fiercely it can't hold onto its own skin, blasting out supersonic winds of superheated gas at over 6 million miles per hour. That's not just solar wind, it's a continuous stellar hurricane, stripping away entire Earth masses of material every year. And yet, despite their violence, these stars are among the hardest to spot. Not because they're dim, but because they're camouflaged beneath coronas of their own chaos. The key to their invisibility lies in their death throes. Unlike ordinary stars, Wolf-Rayet stars have exhausted their hydrogen fuel and begun fusing heavier elements in a desperate bid to stave off collapse. This process churns up carbon, nitrogen, and oxygen, ejecting them into space in thick, turbulent shrouds. From a distance, these expelled gases form opaque cocoons around the star, absorbing its visible light and re-radiating it as infrared, a thermal fingerprint only detectable with specialized equipment. It's like trying to spot a lighthouse wrapped in a thick wool blanket. You might not see the beam, but you'd feel the heat. Take Gamma Velorum, the brightest Wolf-Rayet star in our sky, though bright is relative. Even at just 1,000 light-years away, its visible light is muted by its own expelled carbon veil. Without infrared telescopes, we'd miss the truth. This star is actually a binary system, with the Wolf-Rayet component dumping material onto its companion like a deranged celestial chef force feeding a cosmic patron. But their rarity, fewer than 600 known in the Milky Way, makes them even more elusive. Wolf-Rayet stars exist on borrowed time, their extreme mass dooming them to supernova within a few million years. Some may already be ticking time bombs, their cores poised to collapse into black holes without warning. Here's the chilling twist: their winds might be shaping the universe itself. The heavy elements they spew, carbon, oxygen, even gold, seed future generations of stars and planets. We're literally made of the ashes of these vanishing giants. So while they hide from our sight, their legacy is written in the chemistry of everything around us, from the iron in our blood to the silicon in our planet's crust. Their vanishing act is the universe's most dramatic disappearing trick, one where the magician doesn't just escape the box, but dismantles it with thermonuclear fury. At the chaotic centers of galaxies, stars exist in a realm of perpetual twilight swallowed by the very structures they helped create. Near Sagittarius A, the Milky Way's supermassive black hole, hundreds of stars orbit in frantic loops, their light strained through a toxic haze of ionized gas and dust so thick it dims their glow by a factor of 10,000. These aren't just hidden stars, they're prisoners of gravity dancing in a cage of their own making. Observing them is like trying to spot fireflies through a bonfire. The galactic center's dust clouds absorb visible light relentlessly, forcing astronomers to rely on infrared and radio wavelengths to pierce the veil. Even then, the view is distorted. Imagine looking through a glass of murky water while someone shakes it violently. That's the effect of turbulent magnetic fields and superheated plasma swirling around the black hole, bending and scattering the starlight that struggles to escape. Yet patience and ingenuity have uncovered bizarre residents. Take S2, a star whipping around Sagittarius at nearly 3% the speed of light, its orbit tracing a cosmic racetrack just 17 light-hours across. Its light, stretched and blue shifted by relativistic effects, flickers like a candle in a hurricane as it fights through the surrounding chaos. Then there's the enigmatic G objects, dusty stellar hybrids masquerading as gas clouds until their gravity betrayed their true nature. These chameleons orbit so close to the black hole that tidal forces stretch them like taffy during each approach, leaving trails of glowing debris. The stakes. These stars are more than just cosmic curiosities, they're stress-testing Einstein's theories. Their extreme orbits reveal subtle space-time warps that hint at hidden dimensions or exotic matter near the black hole's event horizon. Some even seem to defy expectations, appearing brighter than physics allows, as if the galaxy's core is magnifying their light like a funhouse mirror. But the greatest challenge lies ahead. The next generation of telescopes, like the extremely large telescope in Chile, aims to chart stars orbiting even closer to the black hole's maw, objects whose light may have traveled 25,000 years only to be scrambled in the final leg of its journey. It's a reminder that the universe's most profound secrets often hide in plain sight, buried beneath the noise of their own neighborhood. And as we decode their distorted signals, we're not just mapping stars, we're reading the fingerprints of gravity itself. There's a special kind of celestial horror lurking near supermassive black hole stars that don't just die, but are unraveled strand by strand in a cosmic tug of war. These are tidal disruption events, the universe's most violent vanishing acts, where a star strays too close to a black hole's gravitational jaws and gets shredded into a luminous stream of stellar spaghetti. The twist: most of these cataclysms happen in total darkness, their light swallowed whole before it can reach us. The physics behind this destruction is both beautiful and brutal. As a star approaches a black hole, the side nearest the singularity feels exponentially stronger gravity than the far side, a difference so extreme it stretches the star like taffy. This tidal force overcomes the star's own gravity, tearing it apart in a process called spaghettification. The resulting debris doesn't just vanish, it forms a swirling accretion disk around the black hole, heating up to millions of degrees and screaming its death throes in X-rays. That's our only window into these events, not visible light, but high-energy radiation piercing through the cosmic gloom. One of the most dramatic examples unfolded in 2018, when astronomers spotted a flare 1,000 times more powerful than a typical supernova. Designated a T2019 KIS, this event occurred when a star roughly the size of our Sun ventured too close to a black hole 26 million times more massive. For weeks, the accretion disk blazed hotter than most stars, emitting X-rays detectable across half the universe. Yet without specialized satellites like NASA's swift and new star, we'd have missed it entirely. The visible light was utterly drowned in the black hole's shadow. But here's where things get stranger. Some tidal disruptions flicker like faulty light bulbs, their X-ray signatures flaring and fading unpredictably. The culprit, black holes with unusually strong magnetic fields, can choke the inflow of stellar material, creating stop-and-go annihilation. Others produce relativistic jets, narrow beams of particles shot outward at near light speed. When these jets point toward Earth, we detect them as gamma-ray bursts, the universe's brightest electromagnetic explosions, the most haunting aspect. For every tidal disruption we catch, there could be hundreds more hidden from view. Black holes aren't tidy eaters. Their messy consumption often buries the evidence in thick clouds of dust. Some may even swallow stars whole, leaving no flare at all, a lightless murder with no witnesses. Yet these grim feasts are more than cosmic spectacles. They're laboratories for extreme physics, revealing how black holes grow and how matter behaves under unfathomable strain. Each flare is a Rosetta Stone, helping decode the invisible dance between stars and the darkness that consumes them. And somewhere out there right now, another star is stepping over the event horizon's edge, its final moments destined to be both spectacular and utterly unseen. Even the mightiest stars can play cosmic hide and seek, especially when they're literally shrouding themselves in their own remains. Red supergiants like Betelgeuse are stellar titans, bloated to hundreds of times the Sun's diameter, yet they wield this immense size against us. In their final throes, these aging behemoths cough up vast clouds of dust and gas, veiling themselves like stage magicians pulling a disappearing act with their own smoke. Take Betelgeuse's great dimming of 2019. For months, the familiar shoulder of Orion faded to just 2/3 its usual brightness, a change visible to the naked eye. Panic rippled through astronomy circles. Was this the prelude to a supernova? the truth was stranger. Observations from the Hubble Space Telescope revealed the star hadn't exploded, it had sneezed. Betelgeuse had ejected a colossal plume of superheated material, 20 billion miles across, which cooled into starlight-absorbing dust. It was as if a lighthouse had wrapped itself in a thick wool blanket, muffling its glow from Earth's perspective. What makes these events so unpredictable is the sheer scale of red supergiant instability. Their outer layers churn like boiling water, with convection cells so vast they could swallow Jupiter whole. When one of these bubbling monstrosities reaches a critical point, it can catapult entire continents' worth of material into space without warning. The ejected matter doesn't just drift away, it lingers, forming a temporary cosmic blindfold that might last months or even years. But here's where modern astronomy turns the tables on these stellar tricksters. Instruments like the Very Large Telescope in Chile now use interferometry to essentially peek behind the curtain, combining light from multiple telescopes to create images sharp enough to distinguish surface details on stars hundreds of light years away. When applied to Betelgeuse, this technique revealed another surprise. The star's southern hemisphere had cooled dramatically, likely driving the dust eruption. It was a stellar fever, breaking an astronomical diagnosis made possible because we finally had the tools to see through the patient's self-inflicted smokescreen. The implications stretch far beyond one star's theatrics. If red supergiants routinely cloak themselves like this, it could explain historical records of vanishing stars that later reappeared, events once dismissed as observational errors. More critically, these dust shrouds might be the universe's way of obscuring supernova precursors. Right now, somewhere in our galaxy, another red supergiant could be wrapping itself in a funeral shroud of its own making, hiding the telltale signs of its impending explosion until the very last moment. So while Betelgeuse's dimming episode was a false alarm, it taught us something profound. The biggest stars don't go gently. They thrash, they cough, they cloak themselves, and in doing so, they remind us that even the brightest celestial landmarks can flicker, fade, or vanish without warning. The cosmos has no obligation to stay visible, and these turbulent giants are the ultimate proof. Some stars refuse to die quietly even centuries after exploding. They haunt the cosmos like celestial phantoms. These are supernova ghosts, the echoes of ancient stellar detonations that linger long after the original fireball has faded to black, the most famous among them. Light echoes, those eerie ripples of illumination that creep across interstellar dust like headlights through fog, reminders of violent endings we missed witnessing firsthand. Take the case of the Vela supernova remnant, a tattered veil of gas glowing faintly in the southern sky. The star that created it exploded over 11,000 years ago, lighting up Earth's prehistoric skies, but without telescopes or written records, the event vanished from human memory. Today, its shattered remains stretch across 250 light-years, visible only because the blast wave still excites surrounding hydrogen to a faint crimson glow. Yet in 2002, astronomers caught a break. Hubble spotted reflected light from the original explosion bouncing off interstellar dust, a delayed encore visible millennia after the main event. This light echo is starlight's last whisper, traveling indirect paths across space just to say, "I was here." But not all ghosts glow. Some supernova leave behind neutron stars, the crushed cores of their progenitor stars, spinning silently in the wreckage. The Crab Nebula's pulsar is a textbook example, but for every one we've found, there could be dozens more hiding in plain sight. X-ray telescopes reveal these invisible cinders by their heat signatures, like finding warm footprints in cosmic snow. One of the creepiest discoveries, the neutron star in the supernova remnant Cassiopeia A. It's there in the X-ray data, a 20-kilometer wide ember cooling from 1,000,000 degrees but emits almost no visible light. Without specialized instruments, we'd never know it existed. The most unsettling part, some supernova may have left no trace at all. early universe explosions from population Roman III stars. Those first-generation behemoths could have birthed black holes directly, skipping the remnant phase entirely. Their only evidence might be the heavy elements they seeded through the cosmos, now locked inside stars like our Sun. We're literally made of stardust from explosions. No one saw ghosts that shaped the universe without leaving a gravestone. Here's what chills astronomers the most. The Milky Way is overdue for another supernova. Historical records suggest one should light up our skies every few centuries, but the last easily visible one was Kepler's star in 1604. Statistically, others have likely exploded since. They're just hidden behind dust clouds or too distant for naked eye viewing. Right now, Betelgeuse or Eta Carinii could be ticking toward detonation, their light already en route but not yet arrived. The ghosts of future supernova are out there, their light traveling toward us like unopened letters from the cosmos. Some of the cosmos' best-kept secrets don't lurk in the void. They hide in plain sight, eclipsed by their own stellar siblings. Imagine a cosmic game of hide and seek where one player shines so brilliantly, its partner becomes nearly invisible. This is the fate of dark binary companions like Sirius B, the white dwarf that orbits Sirius A, the brightest star in Earth's night sky. For centuries, Sirius B went unnoticed, its faint glow drowned out by its dazzling counterpart. But its existence wasn't revealed by light, it was betrayed by gravity's subtle dance. The story of Sirius B reads like astrophysical detective work. As far back as the 1840s, astronomers noticed Sirius wobbling erratically, as if tugged by an unseen force. The math was undeniable. Something massive but invisible shared its orbit. The culprit, a white dwarf, the dense, Earth-sized corpse of a dead star, radiating only a dim afterglow of its former glory. When telescopes finally captured Sirius B in 1862, it was a landmark discovery, proof that stars could fade into near-nothingness while still wielding gravitational influence. But how do astronomers spot these cosmic shadows today? The techniques read like a spy novel. One method relies on spectroscopy, splitting a star's light into a rainbow of wavelengths. Dark companions leave fingerprints in this spectrum, their gravity causing subtle shifts in their partner's light as they orbit. Other times, it's the flickering that gives them away. Eclipsing binaries, where one star periodically passes in front of the other, create telltale dips in brightness. And then there's astrometry, the painstaking measurement of a star's precise position over years, revealing the microscopic wobbles caused by an unseen partner's pull. The Milky Way could be teeming with these hidden duos. Systems like Procyon, another bright star with an invisible white dwarf companion, hint that stellar partnerships often involve mismatched pairs. Some dark companions aren't just dim, they're literal dead stars, their light long faded but their mass still warping spacetime. Others might be failed stars, brown dwarfs too small to ignite fusion, doomed to orbit forever in their brighter sibling's shadow. Here's the twist, these unequal partnerships aren't just celestial oddities, they're cosmic time capsules. White dwarfs like Sirius B are stellar tombstones, preserving information about their progenitor stars' lives and deaths. By studying them, we're effectively reading the diaries of dead suns, learning how stars like our own might one day fade into darkness. So next time you gaze at Sirius, remember, the star you see is only half the story. Its invisible companion whispers secrets about the universe's past and our future. V-838 Monocerotes staged one of the most bizarre disappearing acts in cosmic history, a stellar eruption so mysterious it still puzzles astronomers 2 decades later. In early 2002, this unremarkable star in the constellation Monoceros suddenly flared to over 600,000 times the sun's brightness, outshining the entire Milky Way for a brief, glorious moment. But instead of exploding into a supernova or settling back to normal, it pulled a cosmic bait and switch. The star didn't destroy itself, it swallowed itself, enveloping its surroundings in an expanding shell of dust so thick it vanished from view like a magician stepping behind a curtain of smoke. What made this eruption so strange? Typical stellar outbursts like nova or supernova involve violent ejections of material. V838 Mon's explosion was different. Rather than blasting matter outward, the star's outer layers inflated at staggering speeds, engulfing everything in their path. Hubble's images captured this eerie process in unprecedented detail. Light from the eruption illuminated pre-existing dust clouds like a flashlight beam moving through fog, creating the illusion of an ever-growing sphere. By the time the light echo faded, the star had retreated behind a newly formed cocoon of debris, its surface temperature plummeting to that of a dim red ember. The leading theory suggests a stellar merger, a cosmic collision where V838 Mon consumed a smaller companion star or giant planet. The gravitational energy from this cannibalistic act could have triggered the expansion without a full explosion. Others propose a delayed helium flash, a belated thermal runaway in the star's core after years of smoldering quietly. But the truth is, no model perfectly explains why the star didn't just return to normal or collapse entirely. It's as if V838 Mon rewrote the stellar playbook mid-performance. Today, the star's faint glow struggles to pierce its self-made shroud. Infrared observations reveal it's still there, a cooling behemoth hidden beneath layers of carbon-rich dust, but its visible light has dimmed nearly 10,000-fold since its outburst. The real mystery: what happens next? Some astronomers predict the dust will gradually dissipate, revealing a transformed star beneath, perhaps a blue supergiant or an exotic helium-burning remnant. Others suspect the cocoon might thicken further, sealing V838 Mon away permanently like a cosmic bug trapped in amber, the most tantalizing possibility. We might be witnessing the birth of a new red transient, a rare class of stars prone to violent, sporadic eruptions. If so, V838 Mon could flare again unpredictably, its light bursting through the dust like a prisoner rattling its cage. Until then, it remains astronomy's ultimate sleight-of-hand artist, a star that didn't just disappear, but actively erased itself from the script of the night sky. Among the cosmos' most terrifying hidden predators are magnetars, neutron stars so powerfully magnetic they could erase your credit cards from halfway across the galaxy. These invisible monsters pack the mass of a sun into a sphere the size of Manhattan, spinning with crushing gravity and magnetic fields 1,000 trillion times stronger than Earth. Yet despite their ferocity, they're nearly impossible to spot, silent killers lurking in the darkness, detectable only when they lash out with bursts of gamma rays so intense they briefly outshine entire galaxies. What makes a magnetar's magnetism so extreme? Picture the core of a collapsed star, where protons and electrons have been crushed together into neutrons under pressures beyond human comprehension. Normally, this creates a neutron star, but if the dying star was spinning rapidly with an already strong magnetic field, that magnetism gets amplified beyond reason during collapse. The result is a cosmic battery with magnetic field lines so twisted and tense they occasionally snap like overstretched rubber bands. When that happens, the energy released in milliseconds exceeds what our sun radiates in 100,000 years. The scariest part: we only know about magnetars when they decide to announce themselves. In 2004, a magnetar 50,000 light-years away unleashed a gamma ray burst so powerful it compressed Earth's ionosphere, the upper atmospheric layer that reflects radio waves, rattling satellites and distorting global communications for milliseconds. Had it occurred within 10 light-years, it could have stripped our ozone layer, triggering mass extinctions. Yet before that outburst, the magnetar was just another anonymous speck in Sagittarius, invisible to every telescope. Astronomers estimate our Milky Way could harbor 30 million magnetars, with only 30 confirmed so far. Their stealth comes from their emission profile, Unlike pulsars that broadcast radio waves in predictable beams, magnetars often emit only in high-energy X-rays or gamma rays when they fracture their crusts under magnetic stress. The European Space Agency's integral satellite has caught a few mid-tantrum, their surfaces cracking like eggshells under magnetic strain, releasing starquakes that ripple spacetime itself. One of the most unsettling candidates lies quietly in the constellation Carina. SGR 0525-66 shows no visible light, no radio pulses, just an occasional gamma-ray flicker hinting at the sleeping monster beneath. If its magnetic field shifted just slightly, it could erupt with enough force to fry electronics on every planet in its vicinity. Here's what keeps scientists awake. Magnetars might be the hidden engines behind some of space's most mysterious explosions. Some researchers suspect they could trigger fast radio bursts, those enigmatic cosmic chirps that last milliseconds but defy explanation. Others theorize that ancient magnetar eruptions might explain strange radiation spikes in tree rings from 8th century Earth. The terrifying truth is that we're surrounded by these invisible time bombs, their silent spins counting down to moments of unimaginable violence we can't predict, only witness when it's already too late. Globular clusters are cosmic anthills, dense, ancient swarms where hundreds of thousands of stars are crammed into a space smaller than our solar system's outer reaches. At their cores, stars orbit so closely that collisions are inevitable, and the collective glow is so intense it drowns out individual members like streetlights overpowering fireflies. This is where astronomy faces one of its greatest observational challenges. Stars so hopelessly crowded together they blur into a featureless haze, their identities erased by the sheer weight of their neighbors. To crack this celestial census problem, astronomers deploy a technique called light stacking, essentially playing connect the dots with photons across decades of observations. The Hubble Space Telescope has mastered this art, staring relentlessly at clusters like Omega Centauri or M13, capturing thousands of images that are later combined using algorithms to tease out stars hiding in plain sight. It's like reconstructing a conversation in a crowded room by piecing together fragments overheard over many years. The results are staggering. What appears as a single smudge in ground-based telescopes resolves into hundreds of distinct stars under Hubble's patient gaze, each a pinprick of light separated by less than our solar system's width. But the crowding isn't just a visual problem, it warps cosmic demographics. In these tight quarters, stars interact gravitationally, flinging each other into new orbits or even merging outright. The faintest members, like red dwarfs and white dwarfs, become nearly impossible to distinguish from the glare of their brighter neighbors. Some of the cluster's true residents might only reveal themselves through indirect methods, like subtle dips in brightness when one star passes in front of another. Others betray their presence through X-rays, the telltale signature of a neutron star siphoning material from a companion too faint to see, the most haunting realization. These clusters are graveyards of lost stars. Simulations suggest billions of white dwarfs and neutron stars could be lurking unseen in globular clusters, their faint glow swallowed by the collective radiance around them. Some might be blue stragglers, stars that appear unnaturally young because they've stolen mass from neighbors, their true age masked by cosmic theft. Others could be black holes, hiding in the densest regions where their gravity subtly distorts the orbits of visible stars like invisible hands tugging at marionette strings. What's emerging from these studies is a portrait of globular clusters as celestial safes, their most valuable contents deliberately obscured, requiring the right tools and patience to crack them open. Every new star recovered from the glare isn't just another data point. It's a clue to how these ancient structures formed, evolved, and survived for over 12 billion years. They remind us that sometimes the universe doesn't just hide stars in darkness, it buries them in light. Deep within the swirling chaos of stellar nurseries, newborn stars wage their first battle not for survival but for visibility. These protostars, cosmic infants barely beginning their fusion-fueled lives, remain buried under thick veils of gas and dust so dense they blot out even the fiercest stellar light. The Orion Nebula, that glittering jewel in Orion's sword, isn't just a star factory, it's a fortress of shadows, its most precious creations hidden behind walls of cosmic construction material. To understand the challenge, picture a firefly trapped inside a mattress. That's essentially what optical telescopes face when trying to spot protostars. Their visible light gets utterly smothered by the surrounding dust. But where our eyes fail, radio telescopes become our superpower. Instruments like ALMA in Chile's Atacama Desert don't see light. They detect millimeter wave radiation, wavelengths long enough to slip between dust grains like smoke seeping through a screen door. These radio waves reveal structures optical telescopes miss entirely, spinning disks of material where planets might one day form, jets of superheated gas shooting from the protostar's poles, even shockwaves where stellar winds collide with their dusty cribs. One of ALMA's most stunning discoveries unfolded in the Orion Molecular Cloud Complex, a star-forming region 1,500 light-years away. There, a protostar dubbed HOPS 383 was caught mid-tantrum, a colossal eruption brightening it 300 times in just a few years. To optical telescopes, the event was invisible, but ALMA radio vision captured the aftermath, an expanding shell of heated dust, the protostar's equivalent of kicking off its cosmic blankets. The real magic happens when we compare wavelengths. Hubble's iconic visible light images of the Orion Nebula show glowing gas sculpted by massive stars, but switch to radio observations, and suddenly dozens of previously hidden protostars appear, each cocooned in its own dusty envelope. Some, like the aptly named firework star, HOPS 383's neighbor, flicker unpredictably as they devour material from their surroundings. Others show bizarre asymmetrical disks, hinting at unseen planets already taking shape in the stellar womb. What's truly humbling is realizing these obscured infants are rewriting stellar birth narratives. Conventional models suggested protostars grew steadily, but radio observations reveal fits and starts, violent growth spurts where a star might gulp down Jupiter masses of material in months, then starve for decades. Some nurseries even host failed protostars, objects too small to ignite fusion, destined to cool into planetary mass orphans, the most profound lesson. These dusty cradles aren't just hiding stars, they're actively shaping them. The same dust that blocks our view also regulates a protostar's temperature, determines its spin rate, and likely influences its eventual planetary system. Every time a radio telescope peers through the gloom, we're not just spotting hidden stars, we're witnessing the universe's most intimate act of creation, veiled by necessity but revealed through ingenuity. The darkness, it turns out, isn't empty. It's where the cosmos stitches new stars into the fabric of space itself. Mera variables are the universe's slow-burning firefly stars that flicker in and out of view over months or years, their light waxing and waning like cosmic breathing. Named after Mera, the wonderful star in the constellation Cetus, these pulsating red giants swell and shrink so dramatically they can vanish from naked eye visibility entirely, only to resurge with renewed brilliance centuries later. What makes them extraordinary isn't just their rhythm, it's how they've shaped our understanding of the night sky as anything but static. Mera itself is the prototype, a star whose disappearance in 1638 puzzled astronomers until its return months later revealed the first recorded variable star. Before then, the heavens were considered unchanging, a fixed backdrop to human affairs. Mera shattered that illusion, proving stars could evolve, flicker, or even vanish within a human lifetime. Today, we know it pulses with a roughly 332-day cycle, brightening to magnitude 2 visible to the naked eye before dimming to magnitude 10, vanishing from all but the most powerful telescopes. But the real magic lies in their mechanics. These aging stars are running low on hydrogen fuel. their cores now fusing helium into carbon in unstable bursts. As radiation pressure builds, their outer layers expand to hundreds of times the Sun's diameter, cooling and dimming to a deep red. Then, like a failing engine catching briefly, the star contracts, reheating and brightening again. The process isn't smooth. Shockwaves rip through their atmospheres, ejecting vast carbon-rich winds that will one day form planetary nebulae. Modern astronomy has uncovered even stranger behavior. Some mirrors, like our Hydra, have abruptly changed their pulsation periods, likely due to internal convulsions as they burn through successive fuel layers. Others, like Chi Cygni, exhibit dramatic surface spots, their light curves jagged with stellar heartbeats as massive convection cells rise and fall. Then there's the case of Mera B, a white dwarf companion orbiting so close it steals material from Mera's stellar winds, creating an accretion disk visible only in ultraviolet. What's haunting is how many Mera variables we've likely missed. Historical records hint at lost stars, observed by ancient astronomers, objects like Ptolemy's disappearing star in Scorpius, that may have been Mera's fading before telescopes could confirm them. Today, automated surveys like ASAS-SN scan the skies for these subtle phantoms, revealing thousands of candidates. Yet even now, some pulse unseen in dusty galactic regions, their light absorbed before it reaches us. These stars aren't just celestial oddities, they're mileposts for cosmic distance measurement. They're predictable pulsations helping map the local universe. More profoundly, they're previews of our sun's fate, destined to bloat into a similar variable behemoth before shedding its outer layers entirely. So while they may flicker unpredictably, their legacy is certain, proof that even the fixed stars are anything but, and that the cosmos thrums with hidden rhythms waiting to be decoded. Imagine a star not just hidden by distance or dust, but imprisoned by an invisible cage of primordial black holes, ancient relics from the universe's birth, clustered so densely they warp spacetime into an inescapable labyrinth. This is the fate of stars trapped in dark matter halos, their light bent and swallowed by black holes so old they predate the first galaxies. These aren't just unseen stars, they're celestial captives, locked away in gravitational dungeons we can't peer into. The theory begins with dark matter's most enigmatic candidates, primordial black holes. Unlike the black holes formed from dying stars, these could have sprung into existence in the universe's first chaotic seconds, when dense pockets of matter collapsed under their own weight. Some might be as small as asteroids, others as massive as stars, and if they exist in vast numbers, they could lurk at the hearts of dark matter halos, those invisible cocoons surrounding galaxies. Now picture a wandering star, perhaps ejected from its home galaxy, passing too close to such a cluster. The black hole's collective gravity would seize it, not with a single destructive pull, but with 1,000 tiny tugs, steering it into an orbit so twisted its light could never reach us. What makes this scenario so chilling is the perfect invisibility it creates. Unlike a single black hole's accretion disk or a neutron star's X-ray bursts, a star trapped in a primordial cluster wouldn't emit detectable radiation. The black holes are too small and scattered to visibly disrupt the star, yet their combined influence would act like cosmic quicksand. The star might burn normally for billions of years, its light straining against the warped space around it, only to be bent back inward or absorbed by a passing black hole. Even if it flared violently, the signal would be scrambled beyond recognition like a scream muffled by a soundproof room. The link to dark matter research is tantalizing. If primordial black holes make up even a fraction of dark matter, their clusters could be hiding countless stars across the cosmos. Astronomers hunting for dark matter's fingerprints might already be seeing subtle hints, unexplained microlensing events where invisible objects briefly magnify background stars, or strange gravitational perturbations in otherwise empty regions of space. Some researchers speculate that the mysterious Planet 9 in our solar system's outskirts could even be a primordial black hole, a notion that, if proven, would rewrite our understanding of dark matter's form and distribution. The most unsettling implication: these trapped stars might outlast all others. While visible stars will eventually burn out or be ripped apart in galactic collisions, a star cradled in a black hole halo could survive virtually undisturbed, its light imprisoned but its fusion engine burning steadily in the dark. It's a cosmic irony. The very forces that hide these stars could grant them immortality, shining eternally for no one to see. So as we map the universe's luminous structures, we're forced to wonder how much of the cosmic drama is unfolding in these hidden theaters. The stars we'll never observe might hold answers to dark matter's nature, the universe's infancy, and the ultimate fate of matter itself. They remind us that the cosmos doesn't just conceal its secrets in darkness sometimes, it locks them away behind doors we don't even know how to knock on. Deep within the chaos of the Milky Way's core, a group of stars performs a silent ballet under the watchful eye of a supermassive predator. These are the S-stars, stellar daredevils locked in frantic orbits around Sagittarius A, our galaxy's central black hole. While some, like the famous S2, blaze brightly enough to track, others slip through our observational nets, faint, fast-moving ghosts whose existence we infer more than observe. Their story isn't just about what we see, but about the cosmic hide-and-seek game that reveals the universe's most extreme environments. Tracking these stellar fugitives requires technology that bends the rules of optics. Earth's atmosphere distorts starlight like a funhouse mirror, turning crisp points into blurry smudges. That's where adaptive optics become our cosmic corrective lenses. Systems that measure atmospheric turbulence thousands of times per second, then deform telescope mirrors in real time to cancel out the distortion. The Very Large Telescope in Chile uses this wizardry to spot S-stars moving at 8,000 kilometers per second, their trajectories warped by relativistic effects near the black hole. Without these systems, the faintest S-stars would vanish into the background glow of the galaxy's crowded core. But even our best tools have limits. Some S-stars orbit so close to the black hole's event horizon that their light is redshifted into near invisibility, stretched by extreme gravity into wavelengths our instruments struggle to detect. Others are obscured by the fog of ionized gas swirling around Sagittarius A, their signatures washed out in the same radio noise that once hid the black hole itself. The dimmest candidates, potentially brown dwarfs or stellar remnants, reveal themselves only through statistical analyses of star motions, their presence deduced from the way brighter stars wobble under their subtle gravitational influence. The most tantalizing S-stars might not be stars at all. Some dark objects in the galactic center exhibit star-like gravity without emitting detectable light, possible black holes or neutron stars hiding in plain sight. Others could be binary systems where one partner has been stripped to its core by tidal forces, leaving a nearly invisible skeleton still dancing with its brighter companion. These phantoms aren't just scientific curiosities, they're stress-testing Einstein's theories, their orbits probing how gravity behaves under conditions impossible to recreate on Earth. What's truly humbling is realizing how many players in this cosmic drama remain unseen. For every S-star we track, there could be a dozen more eluding detection, some too faint, some too fast, others simply positioned behind veils of dust. Their hidden motions might hold clues to the black hole's growth history, or even evidence of dark matter's gravitational fingerprints. As our telescopes peer deeper into the chaos, each new S-star discovered, and every one still hiding, reminds us that the universe's most extreme environments are also its most secretive. At the end of a star's life, when it has exhausted its nuclear fuel and begins shedding its outer layers, it doesn't just fade quietly. It transforms into a cosmic sculptor, crafting luminous shrouds so intricate they rival stained glass. These are planetary nebulae, the dazzling funeral shrouds of sun-like stars, where ionized gas glows in ethereal blues and greens. Yet hidden at the heart of these radiant structures lies a secret: the dying star itself, often reduced to a faint, fading ember, a white dwarf, so overwhelmed by its own brilliant ejecta that it vanishes from view without specialized tools. The irony is exquisite. The very material that makes planetary nebulae visible, the ejected layers of the star's atmosphere, lit up by ultraviolet radiation, also acts as a smokescreen, obscuring the star that created it. From a distance, the nebula dominates, its intricate filaments and bubbles glowing vividly. But the central white dwarf, now a Earth-sized remnant hotter than the Sun's core, is often lost in the glare. It's like standing too close to a firework. The explosion blinds you to the tiny spark that ignited it. This is when narrowband filters become our cosmic X-ray vision. By isolating specific wavelengths of light, particularly the doubly ionized oxygen line, O-3 or hydrogen alpha, astronomers can peel back the nebula's brilliance, selectively dimming its glow to spotlight the white dwarf at its core. The technique reveals stars that would otherwise drown in their own aftermath. Take the Helix Nebula, one of the closest planetary nebulae to Earth. To the naked eye, it's a glowing ring with a seemingly empty center. But through an O-3 filter, the faint white dwarf emerges, a pale blue pinpoint holding court in the middle of its self-made masterpiece. Some central stars take deception further. The Southern Crab Nebula He247 conceals not just one white dwarf but two, a binary system where the companion star's gravity distorts the nebula into intricate hourglass-shaped lobes. Without spectroscopy to analyze the subtle Doppler shifts in their light, we'd never know the duo was there. Other planetary nebulae, like Abell 39, appear perfectly spherical, their symmetry hiding turbulent stellar winds that only high-resolution imaging can uncover. But the greatest challenge comes from the oldest planetary nebulae, those whose gas has dispersed so widely their glow is barely detectable. Their white dwarfs, now cooling for billions of years, emit primarily in ultraviolet or X-rays, requiring space telescopes like Hubble or Chandra to spot them. The Stingray Nebula, the youngest known, offers a preview of our Sun's fate. Its central star, though still scorching hot, is fading fast, its luminosity dropping 20-fold since the 1980s. Soon, even its nebula will dissipate, leaving behind a cold, dark crystal of carbon, a black dwarf in the making. The lesson here is humbling. These ghostly shells remind us that stellar death isn't an end, but a transformation, one where beauty and obscurity go hand in hand. The same processes that create breathtaking nebulae conspire to hide their architects, ensuring the universe's most dazzling farewells are also its most mysterious. In late 2020, astronomers around the world noticed something unsettling. The night sky was quietly vanishing. Not all of it, not everywhere, but hundreds of stars that had shone steadily for centuries suddenly began fading without explanation. This wasn't just one or two odd cases, it was a wave, a phenomenon so widespread it earned a name, the Great Dimming. At the center of the mystery was Betelgeuse, the red supergiant in Orion's shoulder, whose dramatic dimming made headlines. But what few realized was that Betelgeuse wasn't alone. Across multiple constellations, stars of varying sizes and ages were flickering as if some unseen hand were turning down a cosmic dimmer switch. Theories erupted like supernova. Some proposed alien megastructures, hypothetical Dyson spheres built by advanced civilizations to harness a star's energy, blocking its light in the process. The idea wasn't entirely new. Back in 2015, KIC 8462852, nicknamed Tabby's star, had shown similar irregular dimming patterns, sparking speculation about extraterrestrial engineering. But the Great Dimming affected too many stars too quickly for that to neatly explain it. Others pointed to vast, drifting dust clouds, cosmic grit stirred up by supernova or colliding molecular clouds. Infrared observations lent weight to this. Many dimming stars showed excess heat, a telltale sign of surrounding dust absorbing and re-radiating their energy. Then there were the astrophysical explanations, stellar tantrums on a scale we'd never documented. Betelgeuse, we later learned, had coughed up a titanic dust cloud, a belch of stellar material so thick it temporarily obscured its own light. But what about the others? Some dimming stars turned out to be eclipsing binaries, their light periodically blocked by faint companions. Others were aging variables like mirror-type stars, their rhythmic pulsations misunderstood until now. The chilling realization, we might have missed previous great dimmings entirely. Before modern sky surveys, a star fading over months could have been dismissed as observational error or atmospheric interference. Even today, with automated telescopes scanning nightly, we're only catching a fraction of these events. The Milky Way could be full of stars that vanish and reappear on cycles we haven't mapped, quietly playing cosmic peekaboo across the centuries. The true lesson of the Great Dimming wasn't about any single explanation. It was a humbling reminder that the universe is far more dynamic, more cryptic than our textbooks suggest. Stars don't just burn steadily until they explode, they stutter, they cloak themselves, they stage disappearances. And sometimes the only hint we get is the flicker of a light that was there yesterday, gone today, and might or might not return tomorrow. Among the universe's most elusive phantoms, dark stars stand apart, not just hidden, but invisible by their very design. Unlike the obscured giants cloaked in dust or the dim remnants fading into cold obscurity, these hypothetical behemoths are woven from the fabric of dark matter itself. Picture a star that doesn't burn hydrogen or helium, but draws its energy from the annihilation of mysterious dark matter particles, glowing not with light but with the heat of unseen interactions. If they exist, they'd rewrite the cosmic rulebook, challenging everything we know about stellar formation and evolution. The concept is as radical as it is elegant. In the early universe, before conventional stars had formed, vast clouds of hydrogen and dark matter may have collapsed together. Under the right conditions, dark matter particles, hypothetically weakly interacting massive particles, could have annihilated upon contact, releasing energy that heated the gas and prevented it from fragmenting into normal stars. The result, a dark star, a sphere of hydrogen and helium powered not by nuclear fusion but by the slow, steady burn of dark matter annihilation. These structures wouldn't just dwarf modern stars, they could grow to millions of times the mass of our sun, glowing faintly with infrared warmth but emitting no visible light whatsoever. What makes these ghosts so tantalizing is their potential fingerprint on the cosmic microwave background, the afterglow of the Big Bang. Dark stars, if abundant enough in the early universe, would have reionized the cosmos differently than conventional stars. Their unique heat signatures might have subtly altered the CMB's polarization patterns, leaving behind clues that upcoming telescopes like the Simons Observatory or CMB S4 could detect. It's like searching for the shadow of a shadow, an imprint of something that never shone brightly to begin with, yet the hunt is fraught with cosmic red herrings. Some anomalies in the CMB, like unexpected cold spots or unusual polarization swirls, have sparked speculation about dark stars' influence, but alternative explanations, primordial magnetic fields or quantum fluctuations from inflation, could account for the same phenomena. The key lies in distinguishing the subtle, telltale signals, a specific distortion in the CMB's power spectrum or a peculiar distribution of infrared background light that no other astrophysical object could produce. The most mind-bending implication, dark stars might not be relics of the past. If dark matter is dense enough in certain regions of the modern universe, like galactic cores or dwarf satellite galaxies, these invisible giants could still be forming today, lurking undetected in the darkness. Their presence might explain gravitational anomalies that defy conventional models, or the unexpected heat radiating from seemingly empty patches of space. And so the search continues, not with optical telescopes peering into the void, but with particle detectors and precision cosmology. Dark stars remind us that the universe's greatest secrets aren't just hidden in the shadows. They are the shadows waiting for us to decode their silent language. Before galaxies, before planets, before even the first flecks of dust formed, there was a star, alone in the darkness, igniting the cosmos for the very first time. This was Population 3, the universe's original pioneer, a titan born from nothing but hydrogen and helium in the crushing wake of the Big Bang. Its existence is theoretical, its light long since faded into the void, yet its legacy pulses through every atom in your body and every shimmering galaxy we see today. These primordial behemoths were nothing like the stars we know. With no heavy elements to help them shed heat, they grew to staggering sizes, hundreds, perhaps thousands of times more massive than our Sun. Their surfaces burned at temperatures exceeding 100,000 degrees, bathing the infant universe in ultraviolet fury, but their brilliance came at a cost. They lived fast and died young, their cores collapsing into cataclysmic supernova, or even direct black holes within mere millions of years. Unlike modern supernova, which leave behind neutron stars or luminous remnants, these explosions were so violent they might have vaporized themselves entirely, scattering their guts across the cosmos in a single, obliterating pulse. The cruel irony, their very deaths ensured we'd never see their like again. The heavy elements forged in their cores, carbon, oxygen, iron, polluted the pristine gas clouds from which new stars formed. Later generations, like our Sun, owe their smaller, stable sizes to this cosmic contamination. Those first stars, in effect, poisoned the well for their own kind, ensuring no future star could ever grow so large or burn so bright. Yet their ghosts linger. Astronomers hunt for them in the faintest whispers of the cosmic microwave background, the afterglow of the Big Bang. Some believe the chemical fingerprints found in ultra-faint dwarf galaxies, ancient relics orbiting the Milky Way, hold clues. These diminutive galaxies contain stars almost devoid of heavy elements, likely second-generation offspring that formed from the ashes of Population 3 giants. By studying them, we're reverse engineering the recipes of stars that vanished 13 billion years ago. The most haunting possibility, we might never find direct proof. The James Webb Space Telescope peers deeper than any instrument before it, searching for the ultraviolet glow of Population 3 deaths in distant galaxies. But even Webb has limits. The universe's expansion has stretched that primordial light into infrared oblivion, and the earliest stars may be forever lost behind an impenetrable curtain of time. Here's the staggering truth: everything we are, everything we see, the iron in our blood, the silicon in our planet's crust, the gold in our jewelry, was forged in the hearts of stars we'll never observe. Their light faded eons ago, but their echo lives on in the chemistry of life itself. They were the universe's first alchemists, transforming simplicity into complexity, darkness into light. And though their fires burned out long before Earth even formed, they lit the way for everything that followed. From Black Widow pulsars consuming their stellar partners to ancient quasi-stars with black hole hearts, we've journeyed through 30 of the cosmos' most elusive wonders, stars that defy detection, not by chance but by their very nature. Each one reveals a different facet of the universe's hidden layers. The dark matter stars rewriting physics, the rogue black holes drifting unseen through galactic alleys, the protostars buried in dusty cradles, and the primordial giants whose light faded long before Earth formed. These aren't just cosmic oddities, they're proof that what we see glittering in the night sky is less than a fraction of what's truly out there. Consider this: for every star visible to our eyes, there could be dozens, maybe hundreds, lurking in the shadows. Some cloak themselves in debris, others emit light our eyes can't perceive, and a few are so alien they challenge our very definition of a star. The universe doesn't just hide its secrets in the voids between galaxies, It tucks them away in plain sight, disguised as empty patches of sky or masquerading as ordinary flickers in telescopic data. And while we've uncovered some of these phantoms, countless more remain beyond our grasp. Their stories written in wavelengths we've only begun to decode. This is the true magic of astronomy. The more we discover, the clearer it becomes. We're not just mapping the stars we see, but learning to search for the ones we can't. Every mystery solved unveils 10 new questions. Are there more dark stars shaping the cosmos? How many neutron stars prowl unseen in our galactic backyard? Could entire populations of stars exist in forms we haven't even imagined yet? The answers are out there, waiting in the dark. So the next time you gaze up at the night sky, remember, the stars you see are just the prologue. The real story lies in the shadows between them, in the whispers of infrared, the tremors of gravity, and the silent pulses of radio waves. The universe is vast, strange, and humblingly opaque. And that's what makes it worth exploring. If these hidden stars sparked your curiosity, imagine what else might be lurking just beyond our sight. Share your wildest cosmic theories in the comments. What unseen wonders do you think are waiting to be found? And for more deep dives into the universe's greatest mysteries, don't forget to subscribe. The cosmos has plenty more secrets to reveal, and we're just getting started.